Yes. Good evening, everyone. Welcome to the seventh session of problem solving for the course Structural Analysis. Am I audible?
Yes.
Thank you. So this is the seventh problem solving session for the course Structural Analysis 1. Let me share my screen. So the concept that we'll be looking at today is the analysis of statically indeterminate structures limited to trusses. So we'll be analyzing statically indeterminate trusses today by the force method of analysis. One of the popular methods among the force methods of analysis is the method of consistent deformation. So we'll be looking at some problems in this. This is one of the most interesting methods in structural analysis. So we'll be solving a couple of very nice problems today. So I hope you'll enjoy the session. So what is the method of consistent deformation? So let me start with a small intro. So we know that for statically indeterminate structures, we cannot determine all the member forces and the reactions by using the equilibrium equations alone. So what is that extra that is needed? We need more. So this we need what are called compatibility conditions. Why? Because the number of unknowns are greater than the number of static equilibrium equations. So we cannot solve for all the unknowns using the equilibrium equations alone. So what we do is we denote the difference between the number of unknowns and the equilibrium equations as the degree of static indeterminacy. And then we solve and then we come up with additional ns number of compatibility equations. So we lack ns equations if we use equilibrium equations alone. So we need to use ns additional equations to solve the problem. Are needed. So how do we solve the problem given a truss? Right. So today we are going to look at trusses. It's a simple truss. So this is a statically indeterminate truss. Right? We have how many reactions do we have? We have 4 reactions. And how many global equations of equilibrium we have? 3. So it's external static indeterminacy is equal to 1. And internally, is it determinate or indeterminate? It is determinate because how many members we have? We have 3 members. And how many joints we have? We have 3 joints. So 6 equations, but that also includes the globally available 3 equations. So internally, it is statically determinate. Now we need one extra equation to solve this problem. So where does it come from? Here we make use of the compatibility conditions. So let me call this A, B, C. Now we don't need 4 reactions to keep this truss stable. We need only 3 reactions. So let us release one of the support reactions. So we release one of the support reactions. So this is fundamentally enough for keeping this truss ABC stable. The additional reaction here, reaction force here, makes the structure statically indeterminate. So let me denote this unknown force as Cx. Now this truss may be subjected to some loads. So this situation can be written as a superposition of this plus this. So we identify that the number of reactors keep the structure just stable. So we denote those additional forces as a redundant force. So this is called a redundant reaction. It's a redundant reaction, and then we denote this additional force as a redundant reaction, and we release the restraint caused by that. So after releasing the restraint, whatever structure we have, along with the applied external loading, is called a primary structure. This is called a primary structure. And this is primary structure with the redundant reaction. So the idea is this. This is statically determinate. So this primary structure is supposed to be statically determinate. Otherwise, there's no use of removing the support reaction. So it has to be statically determinate. And it has to be stable. Once we solve, so the Cx is still unknown. So this is unknown. So we solve this. Suppose under this load, this truss deforms this way. This point moves by a distance, say d, subjected to the applied external load L. So this is L. So suppose the structure under the applied load, if we remove the restraint at this point, the point displaces by a distance dl. But in the original structure, the point is not supposed to displace. What is the condition? We need to apply some extra force, which is supplied by the reaction, which is supplied by the support, to keep the support in place without moving horizontally. So, say under this reaction, if the structure displaces this way, let us call this some delta. Say minus, because it's moving to the left, let us call it minus delta. What is the condition it should satisfy? The condition is dl, the displacement due to the applied load, plus the displacement due to the sorry, you can't take it as minus delta, it will be negative. So if you take the consistent sign convention under this load, what we expect is we'll get a negative so delta measured to the right is positive, which means in this case it is measured to the left. So the delta itself will be of negative sign. So in this case, what is the condition? Since it is a superposition of these two, dl plus delta should be equal to 0. So delta is caused by the reaction Cx, and this is caused by the applied load. Now this will be a function of Cx. So what are the unknowns in this? So this is a known function of Cx. This is a known number. So with this additional compatibility equation can be used to determine what is Cx. So what are the steps to solve the problem? Put them down. Steps. Always, the first step is to determine the degree of static indeterminacy. So first determine the degree of static indeterminacy, NS. Only then you will know how many redundant reactions we can remove. That is the idea. So once you have determined the degree of static indeterminacy, identify the redundant forces. Identify the redundant either reactions or forces. And how many of them should be there? There should be exactly endless number of redundant reactions or forces. Once you have identified, then remove them. Remove the restraint imposed by this endless number of redundant forces or reactions. Remove the restraint. Now, whatever structure you get by removing this extra restraint is called a primary structure. And we have to ensure that the primary structure is statically determinate and it is stable. What is the next task? Next, we need to actually ensure that this we need to ensure that the compatibility is ensured. So that is the equation that I just wrote. dl plus delta is equal to 0. So write down the compatibility condition. Right. So what is compatibility condition? As I said in the last session, it means that the different parts of the structure do not break away or overlap. So we'll see that today. So compatibility condition. Enforce, just write down the compatibility condition. What it is. Then what is the idea? Solve. So find the displacements at the point of action of the redundant force in all cases. Due to both the applied loadings and the redundant force. So once you get a primary structure, you have the applied loading. So this is the point where the redundant force was applied. So find by what this would have displaced if there were no restraint. And then in the second thing, you find what force, if you apply a force here, by what amount it will displace if there was no vertical load. Then superpose both. Then what you should ensure? Substitute in the compatibility equation and so on. So that's it. It's very simple. To make it more systematic, how there is this notion of flexibility coefficients. So let us see what they are. Suppose you have a structure. Can be any structure. It is not limited to trusses. So let me say you have something like this. Say you have a roller system. So this is a statically indeterminate structure to the first degree. So if let me identify points 1, 2, 3, 4. Now let me treat this vertical restraint as the redundant force. So what will be the statically determinate structure I get? This will be my primary structure. So this primary, and there will be some loading. So this primary structure can be using the principle of superposition. This can be related as now this unknown force is usually called so we'll say this is A, B, C, D. This will be dy. But dy is an unknown. If it displaces by delta under dy, what will it displace if I apply a unit load? So if I apply a unit load, it will displace by delta divided by dl. There's a special name to this this quantity that is called flexibility. The displacement by the applied force is called flexibility. And since it is applied at point 4, it is known as F44. Where the first 4 denotes at which point we are seeing the displacement. So this is at which point we are looking at the displacement due to a point load applied at point 4. This is where the load was applied. Load point. So this is delta 4 divided by the force applied at 4. If we extend it, let's remove all this. So 0.1, 0.2. So if you apply a unit load at 0.2, the structure is going to deform in some way. So this will be delta 4 due to a point load applied at 0.2. So this is nothing but F4. Similarly, this displacement is the displacement of the 0.3 due to a unit load applied at 0.2. So this is F3. So this is F22. And one is fixed, so it is called F12, but if in case it is fixed, it is equal to 0. So this is the idea. So we'll be using this very often in our problem solving. Why is it useful? It is useful because you don't need to solve multiple problems. If you know the unit load solution, if you have a different combination of point loads, you can always use the principle of superposition and multiply the loads by displacements by the flexibility coefficient. Sorry, the flexibility coefficient is the displacement caused by a unit load. So if we have some unknown loads or some known loads of a higher magnitude, the displacement is obtained simply by multiplying this the flexibility coefficient by the applied load and then adding them all together. So that is very useful in our problems. I hope it's clear. It will become clearer as we solve some more of these problems. Shall I get it? Any doubts? Okay, I assume there is no doubt. So this is our first problem. Determine the. We add some spaces. So the question asks us to determine the member force in the member AD for the following truss. And for all members, they have a constant E and a constant A. Now, the first step, as usual, is to determine the static indeterminacy, degree of static indeterminacy. So how many reactions do we have? The number of reactions is here we have 2, here we have 2, here we have 2. So the number of reactions is 6. The number of members is 3. And how many joints we have? We have 4 joints. So how many unknown forces we have? In each member, there's an unknown force, and there are 6 reactions. So the number of unknowns is 3 plus 6, which is 9. And how many equations we have? We have totally 2 into j number of equations. So the number of equations is 2 into 4, which is 8. So the degree of static indeterminacy is equal to 1. Is it external or internal? That is simple. If it is, you know how to do it. So externally, you have 6 reactions, and how many? Yeah. So this is a special case. If you separate between external and internal, what happens is internal will be negative. That means without the reactions, this structure itself is unstable. So the internal instability is compensated by the external indeterminates. So in this case, the overall degree of static indeterminacy is 1. You can find out what is the internal and the external separately later. So what can I treat as the redundant member? So if the degree of static indeterminacy is 1, I can treat one of these as the redundant member. So since we have to find the force in member AD, let me treat this member as a redundant member. Now, what will be the primary structure that I'm obtaining? So the primary structure will be the structure obtained by the absence of this force. So if the force in this is absent, how can I make the force in this absent? So let me introduce a small cut here. What happens is right. The extra condition here is this member is continuous. It doesn't have any overlaps or it doesn't open up. So if I relax that condition, this becomes a statically determinate structure. So if I remove this member, what remains is a statically determinate structure. So a cut member cannot transmit any force. So if the member is cut, it means the force in the member is 0. So if a member is cut, it means the force in this member is 0 because it is simple, right? So this space is not subjected to any force. So the reaction here is 0. The force due to this member on this joint is also equal to 0. So, so here the redundant force, you have identified the redundant force as FAD. So that is fine. Now this is so if you have to express this condition as a superposition of two structures, one is this and the other is this. Let me draw this. Now, because of the applied load without the restraint of this member being continuous, what do I have? If this restraint is not there, when it deforms, this member may go this way. It can overlap, causing a mismatch of, say, DL. Now, to correct that mismatch, I'm applying a member force in these two members so that a displacement of how much comes? So this is FAD. What will be the displacement here? You can call it delta AD, but once you have introduced the flexibility coefficients, what can I call it as? I can call it as FAD. The displacement in this member due to a force applied in the same member. So this is the flexibility coefficient FAD. And since there is an applied force, this joint will transmit it and then the forces in all this. So, so now we have two structures to solve for. One is so both are primary structures. This is the primary structure with the applied load, and this is the primary structure with the redundant force. Which is the redundant force? It is FA. So this is statically indeterminate to the degree 1. So it can be solved. There is only one unknown, which is FA. Now let us solve the problem. So in this case, if you look at this structure, what it is nothing but you have a missing member which cannot take up any force. It's very simple to determine what are the member forces. What are they? So if you look at the geometry, this one is 2 meters. And the height is 4 meters. So so we'll see that. So what this is point B, C, and E. Now let us take the equilibrium of joint D for the primary structure with the applied load. You have a vertical force of 20 kilonewtons. Here, let us assume this member is in tension, so we have FBD. You don't have an FAD because you have cut the member. You have cut the member, it is free to overlap or do something, so it will not transmit any force. You have this FCD. And what is the force triangle? So this is 1 and 2. This is 1, this is 2, so this is 5. So in one shot, we can get, and there's a horizontal 33 minutes. So you can get FCD in one shot. What it is? FCD is equal to 30 root 5 kilonewtons. What is FPD? Write down the vertical equilibrium equations. FPD. So it is minus FPD minus FCD by root 5. So this angle, you'll get FCD cos theta, but cos theta is 2 by root 5 minus 20 kilonewtons is equal to 0, which means FBD is equal to minus 80 kilonewtons. That is fine. So let me use the notation capital N for the internal forces due to applied load. And let me use small n for the internal forces due to virtual load. Now what will be DL? Now the task is to find out DL. How do we find DL? So we have already applied a virtual load here. Since we have already applied a virtual load here, we know, no, sorry, we have not applied a virtual load here. We need to determine the displacement, the mismatch created by this removal of restraint. So we can use the principle of virtual work, which is the unit load method. So we can use that. And what do we get? We get 1 acting on DL. This is the work done by the virtual load on the real displacements is equal to summation of all virtual internal forces acting on real internal displacements. Ni, Li, by Ai, Dl. So this is very easy if we use a now we have determined Ni, which is NBD and NCD. So that is obtained. We have NAD and NBD and NCD. Next thing is to obtain the virtual forces small n. But note that applying FAD can be thought of as applying a unit load and then multiplying all the resulting displacements by capital FAD. So let me consider this structure. So in this, let me consider this structure where there is some overlap. I'm applying a unit force. And what will be this overlap? It will be nothing but FAD, AD. And the rest of the structure is the same. Now, do I need to find out the support reactions to solve this truss? So what are the support reactions? Do you think there will be any support reaction at all? No, all the support reactions will be 0. Why? Because this is a pair of equal and opposite forces which are acting along a line. So since this system of forces is self-equilibrating, there will be no support reactions at all. There is no externally applied load. There's no external unbalanced load acting on this truss. There are internal loads. So remember that we have removed a member and then replaced it with the force in the member. So the force is internal, which should be equal and opposite. Internal forces cancel each other. So the reactions, all reactions are 0. So when you look at the virtual structure or the primary structure with the redundant loads, this trick is all the support reactions are 0. So now you look at the joint D. You have 1 kilonewton applied here, this joint D. You have some force coming from here, you have some force. So if you see, enforce horizontal equilibrium of horizontal forces, you will get this as 1 kilonewton. And if you enforce vertical equilibrium, so you know it is 1 plus 1, which is 2. 2 by root 5 into 2, which is 4 by root 5 kilonewtons compressor. So n small n CD is what? Minus, so it is under tension, so it is plus 1 kilonewton. And small n VD is what? It is minus 4 root 5, 4 by root 5. Now again, let us use the formula. How do we do it? So to do this quickly, I have created this Excel sheet. You can just fill in all the values in this. So for question 1, what is AD? Length of AD is, so this is 2 meters, this is 4 meters. So length of AD is square root of 2 square plus 4 square, which is 2 root 5 meters. Length of AD is equal to this. Length of CD is also equal to 2 root 5 meters. And length of BD is equal to 4 meters. So let us fill that in. So the length of AD is 2 into 2 root 5. Length of CD is the same, and length of BD is 4 meters. And what are the forces in that? What is the real applied force? Capital FAD. FAD is 0, right? Because we have removed it. It is cut. What is FPD? FPD is minus 80 kilonewtons. And what is the force in CD? CD is 30 root. So it is 30 star. And what are the virtual internal forces? So the virtual internal forces in AD, it is plus 1. In BD, it is minus 4 by square root of 4. And in CD, it is again plus 1. So we get that the now what is this quantity? So this quantity is nothing but summation of all this. Summation of all this. So this is, and AE I have just taken it as 1, but it doesn't matter because I'll tell you why. So the answer that we get is so what is the real internal displacement? It is summation of Ni, capital Ni, Li by AIA. So this is what we get as 872 point. What was it? 872.433 by AE. Since they have mentioned all the members have the same AE, I can take it commonly out. So I've taken this AE as. So this is a real displacement with no risk. With no risk. And what is F1 or FAAD? What is that? It is the displacement of this point due to an applied unit load at this point. So that is nothing but summation. So 1, which is the applied load acting on FAD, nothing but summation Ni. Again, Ni, because it is the same load point. Where the point where we are finding the displacement is the same as the point where we are finding where we are applying the load. Ni Li by Ai. And what is this value? We got 21.744. This is 21.744. So what is the compatibility condition? The compatibility condition says that the displacement in AD due to the redundant force plus the displacement in AD due to the applied loading should be equal to 0 because there is a restraint. And what is this? This is nothing but FAD into capital FAD plus DAD equal to 0. Now what is capital FAD? Capital FAD is nothing but minus VAD by FAD. So what is this value? Let us find out. So let me call this. So it's nothing but 40 point. So let us see if our answer is here. Yeah, so the answer is C, 40 point. Is the procedure clear? I hope it's clear. Let me go to the next question. So this is a similar problem. Here the indeterminacy is external. So what are the, let us find out. The degree of external indeterminacy here is we have 4 reactions minus 3 equilibrium equations, which is 1. And what is the degree of internal indeterminacy? How many members we have? 1, 2, 3, 4, 5. 5 members minus how many joints we have? 1, 2, 3, 4. 2 into 4 minus 3, which is 0. So internally it is determinate, externally it is indeterminate. So what we have to release is a additional support reaction at the points. So let me consider the primary structure as this. So let me consider a primary structure like this. So first I'm applying a load onto this. The applied load onto this. Let me call it P. And under the applied load, it deforms this way. Let's also load here. This I call it as D at the point 1. Let me call this degree of freedom as 1. Plus, let me take the reaction on this structure at the point C in this direction. And how much force I should apply? I should force Cx. And because of this, say the structure deforms in a different time. But how much it will deform? It will deform to a value of Cx into F11. Because I've taken this point as 1, I can call it as F2. Now, what is the compatibility condition that I should write down? It is D1 plus Cx into F11 equal to 0, which means Cx, which is what we need, the horizontal reaction at the support C, that is nothing but minus D1 by F1. Now the task is to determine what is F11 and D1. So as usual, let us solve the primary structure. So in the primary structure, we have is 30. This is vertical. Here I'm applying 20 kilometers. So you know these two members are horizontal, which means if you take C. So if you take the joint B, there's only one vertical unknown force. So this will be subjected to a tension of 20 kilometers. And if you go to point D, there are two one more thing that you can say is the structure is symmetric. So it is symmetric about the point B, symmetric about this line, which means the both the reactions, once you have removed the support reaction, once you have removed the horizontal support reaction at the point C, the structure becomes symmetric. So the support reactions will be equal. What will they be? So 30 plus 20 is 50. So the reactions you get will be, you can replace I can replace them with will there be any horizontal force? No, because after you replace it with a roller, there's only one support reaction and there's no applied horizontal loading. So it is 0. Now, if you take the equilibrium of the joint A, you have a vertical force of 25, and this, which means, and this is a 45 degrees triangle. So what will be this force in the member AD? It will be under a compression of minus 25 root 2. Due to symmetry, this member will also be under a compression. Coming to the point A, the only unknown remaining here is AB. Since it is a 45 degrees thing, line, so you get central tension of 25. Central 25. So that's it. Let us fill in the table for problem 2. So what is the member force in the member AD? Let's fill in the lengths first. So 4, which means AD will be 4. This is 4 square root of number DC is also of the same length. So you can number CD is also. What is BD? BD is 4 meters. 4 meters. GC is 2 meters. Again, AE is constant for all the numbers. E is 100 and A is not affect our results. Whatever it is, if it is constant. Sorry for the interruption. Due to a power issue, I could not continue on that. So that meeting got ended due to as the internet went away. I'm proceeding with my mobile hotspot. So I forgot to record the last question. Let me just quickly go through it. So this is the primary structure. We had already determined the unknown forces, and similarly we also took the redundant. We took the primary structure with the applied redundant force. By simple analysis, we found that except the two horizontal members at the bottom, all others are zero force members. Then we just fill in the data for question 2 as we did earlier and determine the unknown reaction force. So this gives the displacement due to the applied loads, and this gives the displacement due to a unit load applied at the point of reaction. So divide this by this, we get the answer to be minus 25 kilonewtons. Now in problem 3, we are again asked to determine the member force in the member AD. So to determine that, we cut off the member AD as we did in the first problem and replace it with a combination of two structures where one is the primary structure with the applied load and the other is the primary structure with the extra force FAD. So here we have FAD. So by how much this mismatch will happen? So here the mismatch will be equal to small f 1 FAD. Let me take it as just F1, capital F. Take it as F. Or FAD, no problem. And here in this case, let this applied force create a mismatch of D1L. So simple. So we were analyzing the primary structure under the applied vertical force of 25 kilonewtons. So this will be a zero force member since there's no horizontal force. This will be minus 25 kilonewtons. And this, there is no other force in this. So the vertical force will be, so here it is compressive. So this will be tensile 25 root 2. So 45-degree triangle. So this is 25 root 2 tensile. And this will be 25 compressive. And here we have a downward force of 25 kilonewtons. So what will be the reaction that comes onto this? So the reaction will be again 25, which is equal and opposite to this force. And what will be the horizontal force? The horizontal force will be 0. Note that this member does not exist. So this member is cut off, right? So this doesn't carry any force. Don't get confused with this. So this is a zero force member, this is a zero force member. These two members have this much. Plus this. So we have found out what are all these capital N's. Now let us find out the small n's. How do we do that? We apply a unit equal and opposite force, which is 1. And as I already said, we don't have any support reactions. So if it is 1, since it is 45 degrees, this will be minus 1 by root 2. This will be minus 1 by root 2. This will be minus 1 by root 2. All are compressive. This will be minus 1 by 2. Only this one will be. So when you subject it to 1, the resulting force has to be, resisting force has to be this, and this at 45 degrees. So this will be minus 1 by root 2, minus 1 by root 2. At this point, when you come, you have a vertical force of minus 1 by root 2. So to resist it, the diagonal it has to be 1. This will be minus 1 by root 2. So this is very simple. You can get this. So now we have the small ends as well. What is the next step? Find out the D1L and F1. So let us fill in the values. So AD is of length 3 root 2. 3 star equal to 3 star. And BC is also of the same length. BC is also the same length. All other members are 3 meters. And what are the forces? The member force in AD due to the real applied loads is 0, right? It is 0. In BD, what it is? BD, it is again 0. And what is it in CD? It is minus 25. And what is it in what is the next thing? AB? AB is again 0. And what it is in BC? BC, it is 25 square root of 2. And then finally, what is the member force in AC? It is minus 25. We have also got the small n, which is the member force due to virtual unit load. So when you apply a unit load, the member force in AC is 1, tensile 1. That is what we applied. Sorry, not AC, AD is 1. And in BD, what is it? BD, it is minus 1 by root 2. Not only in BD, in DC, in BD, DC, CA, AB. So BD, DC, C, where is CA, AD, BD, CD, CA is this, and AB. And again, this one has a force of. So that is simple. So we get D1L, which is the summation of all these, as 256. So we get D1L is 256.06 by A. By A. And what is F11 or FADAD? That is 14.485. Right? So what is the reaction? What is the force in the member AD? Note that both are positive, which means. So what is the compatibility condition that we got? It is D1L plus FAD AD into force in the member AD is equal to 0. Which means capital FAD is minus D1L by FAD. So what it is? Equal to this divided by this. 17.68. So the answer is B. So this is equal to minus 17.68 kilonewtons. Note that it is compressive, and that is what we expect. Since there is a vertical force coming at this point, this will be under compression. And this will be under tension. So those are fine. Let's go to the next question. Yeah. It's good. The power is back. Let me turn on my video. Now determine the horizontal reaction at support A for the following truss. For all the members, E and A are constant as usual. So again, now let us determine the degree of static indeterminacy. So NS internal. Internally, you can easily see it is a determinate structure, right? You have how many members? 1, 2, 3, 4, 5, 6, 7. 7 members and how many joints? 1, 2, 3, 4, 5. So 2 into 5 minus 3, 0. So internally it is determinate. Externally it is 4 minus 3, 1. So it is statically indeterminate to the first degree. So what is that you treat as an unknown reaction? The redundant reaction is horizontal reaction at the support A. AX. As usual, let us release AX and construct a primary structure. So this is our primary structure. And we can decompose the given situation into a superposition of two cases, where in one case, you have the reaction acting here. Just A, let me call it, let me just call it as X, right? It's an unknown. So let me call it as X1 and say this displaces by F11 X1. Here we have the other A, B, C, A, B, C, B. I have 30 kilonewtons acting here and 20 kilonewtons acting here. Now that's it. We can first step is to, as usual, determine. So this is our structure 1. This is our structure 2. So in structure, so what is the compatibility condition? The compatibility condition is, so in this structure, suppose it displaces by say D1L. Here it's F11 X1. Compatibility condition is D1L plus F11 X1 is equal to 0. Fine. Now let us determine the forces in these members. So as always, the first step is to determine the unknown reaction. We remove these supports and denote. So there's only a vertical force here. There's an unknown horizontal and vertical force here. Same thing goes here. Let it be. So let me take moments about the point B, okay, because there are two unknowns here. If we take moments about the point B, so take it is sigma MB should be equal to 0, which means A acting at 2 times the distance. So this is 4 meters, 4 meters. So A acting at 8 minus 20 acting at 4 plus 30 acting at 4 equal to 0. So A is nothing but 20, 10, 40 by 8, which is 5 kilonewtons. So here we have an upward force of 5 kilonewtons acting, which means this will be subjected to, this is a 45 degrees triangle. So this will be subjected to a compression of 5 root 2, which means this will be subjected to a tension of 5. So coming to this joint, what are the unknown forces? So there is no other external force acting at this joint. So you have 5 root 2 acting at 45 degrees. So if you draw the force triangle, you have minus 5 like this. To resolve it, you'll have minus 5 like this. And this is the only other horizontal member. So this will be under a compression of minus 5. Similarly, the vertical member will be subjected to a tension of 5. So that is very simple. You just consider this joint. There is 5 root 2 acting here. And you have some unknown forces in these two directions. So the resultant has to pass through this. So this has to be a downward force. This has to be a leftward force. So this is 5 and this is 5. Simple. Now let's come to this joint, right? So in this joint, there are two unknown forces, and other forces are all known. So it's easy to solve. So what is the net upward force acting at this joint? So let us take the joint C here. So in joint C, you have 5, you have 20, you have 5, and you have two unknown forces like this. So If you determine the vertical, it is easier. So what is the vertical force? Total vertical force is 15. So 15 downwards, the total vertical force is 15 downwards, which means this should be subjected to 15 root 2 along the line. So this is subjected to a tension of 15 root 2. And horizontally, what is the thing? So you have 5 in this direction, 15 root 2 by root 2. So 15 in this direction. So this should be, so this is compression. Remove this. So this is subjected to 10 in this direction. Compression of -10. So this is the joint C. Coming to point E, everything is known. So you can simply check. Just a minute. Something is not correct here. So this joint, what do we have? We have 20. Is this 15 to 15 root 2? Let me check. Something is not quite correct. Sorry. A is -5, right? So A plus 5 is A 8A plus 40 equal to 0. So this is minus. So all these forces are reversed in direction. Sorry about this. So this is a downward force and this is positive. This downwards is positive. So this is under a tension of 5 root 2. So this minus 5 is under a positive tension of 5 root 2, which means this is also positive tension. And here this is also under, so you come to this joint. So the reaction, the upward is, it's like this. So this has to be under compression of -5. And coming to this point, we have a downward force of 5 root 2. So the upward force should be, this should also be under compression of -5. So coming to this point, we have 20 downwards, and this is also 5 downwards. So this is -5 upwards, so this is 5 downwards. So the total vertical force will be 25, and this will be 25 root 2 upwards. So here, if you have a tension of 25 root 2, I already have a tension of 5. So what is the total? So 25 along the horizontal plus 5, which is 30. So that is satisfied. What is the vertical force? So this is 25 root 2, which means the vertical force will be compressive 25 minus. So this is plus, this is minus, this is plus, and which means the reaction here is also 25. The horizontal reaction is Horizontal reaction is nothing but the total horizontal force, just 30. Oh, wait. 30, which means this force which we determined earlier is also, it's not -10, it is -30. So this is the force system. Sorry for that mistake. This is downwards 5. So this is -5. This is positive. This is negative. This is positive. This is negative. This is negative. Now let us fill in the values into our table. So, to question 4, what is the length of the member? What is the length of the member AD? AD is 4√2. AD is equal to 4√2. Next one is ED. What is the length of the member ED? It is 4. CD. CD is vertical, so again it is 4. DE is 4. Oh, wait a minute. We can't have a DE again. So 1, 2, 3, 4, 5, 6, 7. It's not DE. It should be this AD, CD, AD is fine. BC, AC, BC, AC, CE. It is B. B is again 4. BC is 4. AC is 4. And CE is 4 with 2. What are the member forces? AD, it is 5√2. ED, it is 5. CD, it is -5. BE, it is -25. BC, it is -30. AC, it is -5. And finally, CE is 25√2. Possible. Fine. Now let us solve the redundant structure. Again, in this case also, it is very simple. We have so the redundant structure is just this. We have a unit load acting here. This is the only support reaction. So this is the only horizontal reaction. So this is something like this. What will there be any vertical force? No, because the horizontal forces are acting through along a straight line. So all vertical forces are 0, which means there's 0 force in all these members. And what is the member force in this? Compressive. Compressive. And what are these members? It is A, C, and B. So except AC and BC, all other capital N's are 0. So AC is AC. AC is -1. And BC is -1. All others are 0. Now what we get is the D1L. What is D1L? The displacement due to the applied loadings at this point. That is equal to 140 by AE. And what is F11? It is summation Ni Li by AIEL. And that we got as 8 by AE. So therefore, yeah. So therefore, what is D1L by F11, which is, so what is the compatibility condition? It is D1L plus X1 F11. So D1L is here, F11 X1 is here. Sum of both should be equal to 0 because this is a hinge support, which means X1 is equal to minus D1L by F11, which is minus 140 by 8, which is 140 by A gets cancelled. So 70, 35, 17.5 kilonewtons. So since it is minus, it means the force is acting towards its left. It's not acting towards its right. That is obvious because the applied horizontal force is in the right direction. So this should be left 17. So the correct answer is B. So let's go to the next question. Determine the horizontal reaction at the support C for the following truss. All the members are having the same AE and two diagonal members are not connected to each other. Here we have to be a bit careful because the all the members are not having the same AE. That's important. They are having different AEs. They're not having the same AE. So we have to be a bit careful. So let us first fill in these AE values. So for let us for question 5. Let us fill in the given data. What are the members? First AB, BD, DC. So we'll have AB, BD, DC, then CB and AD. CB, then AD. So AB, BD, DC all have the same length, which is 5 meters. This is 5, 5, 5. This is 5 root 2, 45 degrees. And this is the same. What is AE? For the member AB, it is just 1A. So let it be 1. For the member BD, it is 1.5. So let me take this as 1.5. The idea is to take AE commonly out so that our answers don't have to depend on this A and E, these particular numbers. Only the factors matter. DC is 2. CB is 1.75. And what is AD? AD is 1.25. This is fine. And now we next step is to, as usual, solve. So what are the unknown? So again, static indeterminacy. So NS, as you easily see, external it is 4 minus 3. And internal what it is? How many members are there? 1, 2, 3, 4, 5. 5 minus how many joints are there? 1, 2, 3, 4. So 2 into J, 4 minus 3. So it is equal to 1. So it is externally indeterminate to the first degree. So what is that we should release? They're asking the horizontal reaction at support C. So let us release the horizontal reaction at support C. So the primary structure that we get will be something like this. And we have an applied load of 30 kilonewtons here. And here we have an applied load of 50 at an angle 60 degrees. Let me resolve it along the horizontal and vertical components. So cos 60 is half. So this is 25 kilonewtons. And sine 60 is root 3 by 2. So this is 25 root 3 kilonewtons. And because of this, let us suppose the support moves by D1L. This has to be superposed with the action of the redundant reaction force. So in this case, let us assume the unknown reaction force to be x1. Acting in this direction. And what will be the resulting displacement? It will be F11 times x1. Now let us solve the two structures. So here we have, we can start anywhere. So first step is as usual to determine the unknown support reactions. The unknown support reactions in this case are, if you take moment about the point A, the structure. So if you take moment about the point A, so this is B. So if you take moments about the point A, we get Cy acting at 5 meters, minus 25 acting at 5 meters, minus 25 root 3 acting at 5 meters, equal to 0. So Cy is nothing but 25 into 1 plus root 3 kilonewtons. Fine. So at this point, we have a vertical force of 25 into 1 plus root 3. So at the joint C, we have a vertical force of 25 into 1 plus root 3. And what is the horizontal force? Horizontal force is 0, which means this member is a zero force member. Because FBC cos 45 plus 0 is equal to 0. So this means it is 0. And this is having a, let me check. Yeah, correct. So this member is subjected to a vertical force of 25 into 1 plus root 3, which means this is under compression. It's under compression. Minus 25 into 1 plus root 3. Coming to this point, right? We have two unknown forces. We can solve for it. Or this is even easier. So if this, if you look at this is a zero force member, which means at this joint it is effectively only this, which means this is a zero force member, and this will take up the entire 30 kilonewtons. So this is subjected to a compressive force of 30 kilonewtons, which means the reactions of the 30 kilonewtons. No, we don't know what is the reaction, but what will be the horizontal reaction? Since there's no other horizontal force, the horizontal reaction at this point should be equal to 25 kilonewtons. This is 25 kilonewtons. Which what is the force in this member? There is no other member connecting it, so this will be 25 root 2. So this will be subjected to 25 root 2 tensile. Now let us check at this point if everything is satisfied. So this is a zero force member, it's 30. So this is 25, and that is taken by this member only. This is 25 by root 3 downwards, and there's another 25 acting here. So totally it is 25 into 1 plus root 3 upwards. So everything is fine. The structure is in equilibrium. As usual, let us fill in these values into the Excel sheet. So what is the member force in the member AB? 30 minus 30. BD 0. DC minus 25 into 1 plus root 3. So it is equal to minus 25 to 1 plus square root of 3. And for the member CB, it is 0. And for the member AD, it is 25. For CB, it is 0. And for the member AD, it is tensile 25 root. Now it's time to determine the virtual internal forces due to an applied unit load. So let me take a unit load applied here. Right? Just to, I'll mark it in green so that you know it is because of the unit load. So let me apply a unit load here. If I apply a unit load, what will be the force in this? Simple tensile √2, because this is at 45 degrees. Vertical will be compressive to resist the compressive. You can't see that, right? There is a reaction here. So we'll see. So here it will be, the horizontal reaction will be 1. And if you take the total structure, there are no vertical forces. So the vertical reactions are 0. Which means this vertical force will be nothing but compressive -1. Coming to this point, again, due to this, there is a tensile √2. Vertical will be compressive. So again, these two tend to compress this strut. So this will be, what are the, is A, B, B, C. So except AD and BC, all others are subjected to -1. Okay. So AD is square root of 2. And BC is also square root of 2. All others are subjected to. So what is the D1L we get? D1L is 603.59. So D1L, this is equal to 603.59 by AE. Remember, we have factored out all the AE. So it doesn't really matter whatever AE is, but the distribution matters. Only these factors we have included with the understanding that we can take the factor AE commonly out. And F11 is 30.228. So F11 in this case is 30.228 by AE. Both are positive, which means the reaction at C that we have determined is, so what is the condition, compatibility condition? It is D1L plus F11 X1 is equal to 0. And X1 is equal to minus D1L by F11. So which is determined that it is .96. But some let me check. So this is √2, √2, -1, -1, -1. Fine. Here it is. Here something is going on. Check. So here is 25 acting at 5. Sorry, we missed this 20 kilometers. So this will be 20, 25, 20. So this will be 25 into 1 plus √3 plus 20. 25 into 1 plus 20. So this becomes minus 45 plus 25 root 3. And at this joint, this is no longer a zero force member. This is zero force. So this will be subjected to not zero. This will be subjected to minus 7. That's it. And since this remains a zero force member, that's not an issue. So but since there's a 20 acting here, you need to consider this. So this is compressive 20. So the total rightward force on this joint is 20 plus 25, which is 45. So this force here should be 45. And this will be 20 plus 25, which is minus 45. Sorry about it. Now it is all right. Let us make these corrections in the Excel sheet. So this is 25 into 1 plus root 2. There's another 20. And this is not 25 square root of 2. This is 45 root 2. In the member BD, it is not 0, it is subjected to a compression. This the answer that we get D1L is 946. 946.5. And F11 is 30.22. F11 there's no issue. F11 remains the same. So this the ratio becomes 31.3. This is minus 31.33 kilometers. Which direction it acts? You assume rightwards, but it turns out to be negative, so it acts leftwards on the structure. That's again obvious since the applied loads are all towards this. So the answer is D, 31.3. Yeah, next we have a problem in which will have two unknown reactions. So it will result in a 2x2 system that we need to solve. Before we proceed to that, let me know if there's any doubt or an issue. Okay, let me proceed. Now we are asked to find out the member force in member CD of the given truss in question number 5. So once we have already determined the forces in the primary structure and also in the redundant structure, the member force in CD will be. So this is a perfect superposition. If you scale the unit load by magnitude x1, all the internal forces also get scaled by the same scale. If I apply x1, so let me use a different color. If we apply x1 instead of the unit load, the internal forces will all be in the same direction, just they'll be scaled by x1. To x1. Now, what is the total force? Total force can be obtained by superposition. So it is minus 45 minus 25 root 3 minus 1 into what is x1? X1 we determine it as minus 31.3. So the answer is you compute this, you get so this becomes positive. We'll get 31.3 minus 88.30. Which is the force in the member C. And this is nothing but minus 56.98. So the correct answer here is 56.98 compressive. Now let's go to the next question. So calculate the degree of static indeterminacy of the following truss. So we have done it several times. So external, what is the degree of external indeterminacy? NSE is there are 4 reactions and 3 equations of static equilibrium. So the difference is 1. And what is the internal degree of static indeterminacy? It is how many members do we have? 1, 2, 3, 4, 5, 6, 7. There are 7 members, which means there are 7 member forces which are unknown. And how many joints do we have? How many equations we have? We have 2 at every joint. So there are 5 joints. Wait, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 members. And exclude the 3 global equations. So you get 1. 8 minus 7, which is 1. So the total degree of static indeterminacy for this problem is 2. And there are 2 unknown redundants, and one of them is internal and the other is external. So the correct answer is 2. Now the next step is for this given problem, we are asked to determine the flexibility matrix. So we'll see how to do it. So to solve the problem of question 7 using the method of consistent deformations, we are asked to solve the equation d1l d2l plus this matrix equation. And the unknowns are specified as the vertical reaction at support A and the member force in the diagonal member AD. So here, the way we define the flexibility coefficients are such that the first unknown redundant is the vertical support, and the second unknown redundant is the member AD. So let us draw the primary structure. So the primary structure we get is go to the previous page. So we need to remove this member AD, and we need to remove the vertical reaction at the point A. The structure we get will be so you can quickly check that this is a statically determinate and stable structure. So this is our primary structure. And the given loading conditions can be always represented as a superposition of the applied load. So the applied load is 40 kilonewtons at an angle 36.87 degrees. So this is 36.87 degrees. So the tan of this angle quite common. It is 3/4, which means the horizontal component of the load is 3/5 times 40, which is nothing but sorry, the horizontal component is 4/5 times 40, which is 32. The vertical component is 24. So let me represent the inclined load as a combination of these two. So there's a vertical force of 24, horizontal force of 32 at this joint. What is the joint number? So this is A, B, C, D, and E. So this is one primary structure subjected to the applied external loading. Plus, now we need to apply the removed reaction. So let me call this redundant structure 1, R1. So there is a removed member here that is represented by this internal force x1. Oh, sorry, this is not x1. First one is the vertical force. This is x1. The second redundant structure is due to the removed diagonal moment, x2. Now, what is the compatibility condition in this case? The compatibility conditions are that the mismatch in the first compatibility condition is that the vertical displacement of the point A due to the superposition of all these cases should be equal to 0. Which means, let us say under this condition, the joint A displaces by d1L. And there's a mismatch of d2L in the vertical in the diagonal. And in the second case, when you just apply only the vertical reaction, let us say it displaces by what? It displaces by f11 x1. And what will be the mismatch that occurs here? It will be f21 x1. So it is the displacement at the point 2 due to a unit load applied at the point 1. And here what will be the case? Here we have an upward displacement of f1 to x2. And the mismatch that occurs here will be f2 to x2. So the compatibility conditions in this case will be d1L plus f11 x1 plus f12 x2 should be equal to 0. And the other mismatch should also be 0. So d2L plus f21 x1 plus f22 x2 is equal to 0. These two conditions are precisely what are represented by this matrix equation d1L d2L. This F matrix acting on X is equal to 0. Now the case is the same. So let us just get the Excel sheet ready. So we have total members. We have AB. We have AB, BD, DC. So AB, BD, DC. And we also have an AC. We have AC. And then BC. So BC is the we have AD. And then DE and EC. And all of them have the same cross-section properties. But you have two virtual forces. So these are the internal displacements due to the virtual force 1. And let me insert a column here. This is N1. N2. So this is nothing but N N2 L by A. So that is it. So what is N1 L by A? So this is equal to this star N1 star L by A. And this is equal to N star into star L divided by A. This is equal to N1 star L divided by A. And this is N1 N2 and this is N2 N2. So N1 N1 is this star is okay. This is N1 star N2 star L by A. In this case, it is N2 star output. So now let us fill in the length values. What is the length of AB? It is 4 meters. So AB, BD, and DC are 4 meters as usual. CB and AD are 4√2 meters. And then we have DE. AC is 4 meters. DE and EC. DE is 4√2. AC is 4 meters. So E is. So let us, as usual, solve the problems. So the primary structure, let us determine the unknown forces. So we have 24 vertical. So let me use a different way. We have 24 vertical, which means the force in this member will be equal to 24√2. So this is subjected to a compression of 24√2. What is the horizontal force? So there's a 24 coming onto this. So 24 plus 32. What is it? So 24 plus 32 is um, So this will be tensile 56. Coming to this joint, there is no vertical force. So this is a zero force member. Not only that, this will be exactly 56. And there is no other vertical reaction. So the vertical reaction at this joint should be 24. And since what will be the horizontal reaction? So let us determine that. When we come to so to determine the horizontal reaction, let us take moments about the point A. Sigma m A equal to 0. If you take moments about the point A, you get dx acting at 4 plus 32 acting at 4 plus 24 acting at 4 equal to 0. So therefore you get dx as equal to minus 56 kilonewtons. So here it is minus 56, so it means it is tensile 56. Since these two are balanced, the horizontal, there's no other horizontal force to be there. So the horizontal component of the force in this member is 0, which means the force in this member is 0. And sorry, 24 acting at 8. Sorry, so 48 plus 32 is 80. Dx is minus 80 kilonewtons. So Bx acting at 4 plus 32 acting at 4 plus 24 acting at 8 equal to 0. So Bx is equal to divide through by 4, we get minus 32 plus 48. So 32 plus 8 is 40. 40 is 40 is 8. So this is minus 80 kilonewtons. Which means what is the deficit? So the horizontal force 80 minus 56 is 24. So this diagonal member is subjected to a tensile force of 24. So this is tensile 24. Now you see that the forces at this point are balanced. The vertical force is 84, 80. Okay. What will be the horizontal force in this member? It will be 0. And what will be the vertical? Sorry, the member force of AB is the force in the member AB is 0, and here, what will be the force? So 80 is already taken back. So this will be subjected to a upward force of 48. Which means this is subjected to a compression of 48. Now check the equilibrium of joint C. You have 48 and you have 24 root 2, 24 root 2. So this is fine. So 24 plus 24, 40. So the equilibrium of joint C is satisfied. Let us fill in the values as usual. The force in the member AB, the real force in the member AB is 0. PD, it is minus 56, or no, sorry, 56. DC is 0. CB, it is 24 root 2. And then AD, it is 0 because that is released. AC, it is minus 48 kilonewtons. So there's a minus here. DE, it is tensile 56. And EC, it is minus 24 root 2. Now let us solve the virtual forces structure. In this, so you can quickly recognize that there's only a vertical force applied here. And this is this joint is having two non-collinear members meeting at a point which doesn't have any load or reaction. So these two are zero force members. Again, coming to this joint, you have something at perpendicular. So if you enforce equilibrium equations, this is 0, this is 0. Coming to this joint, you again have two members that are non-collinear subjected to no loads. So these two are also zero force members. So finally, the only member that is stressed is this. You're applying a vertical force of x1, or if you apply a unit vertical force 1, this will be subjected to a compression of -1, and there will be a downward reaction. So except the member AB, all others have 0. Except the member AB, which is having my force of -1, all others are 0. Similarly, let us solve N2. So again, it is a self-equilibrating force. So if I apply a unit force in the unknown member, what will be the forces? Simple. We have already done this. This will be -1 by root 2. And this will be -1 by root 2. Again, these two are known to be zero force members. Coming to this joint, you have -1 by root 2 this way. So this should be subjected to a tension of 1. This will be -1 by root 2. This will be -1 by root 2. So it is very simple. We have in AB, BD, DC, and CA. So AB, BD, DC, and AC. We have -1 by root 2. What is the force in the members AB and BC? AD and BC. AD it is 1, and BC also it is 1. Tensile. So 1. DE and EC are known to have zero forces. So therefore, what is the total course we have. So now let us determine what are the flexibility coefficients. So using the principle of virtual work, we know that 1 dot F11 is equal to summation N1 L by A over all members. Similarly, 1 acting on F12, which is the displacement due to the unit load, is N1 N2 L by A. 1 acting on F22 is nothing but N2 N2 L by A. We have still not input the length of these members, so yeah, that is fine. So this N1 L by A, the summation of that is 4. So we get F11 is equal to 4. What is F12? We'll see that N1 N2 L by A, which is 2.8284. That is 2.828. And what is F22? F22 is nothing but N2 L by A, which is 19.313. So it is 19.313. Now, if we arrange it in a matrix, we get 4, 2.828, 2.828, 19.313. So this is our flexibility matrix. What does it match with? So 4, 2.828, 2.828, 19.3. So this is the correct answer. Now let's go to the next question. We have already solved for this. Find out the matrix D1L, D2L. So how to determine that? So we know that D1L is by the principle of virtual work. It is sigma the internal virtual forces caused by the unit load acting on the real internal displacements NL by AE. And what is that value? Capital N N1 L by A. This is 0. It is 0. And what is D2L? Same thing. Summation N2 NL by AD. N2 NL by is 169.37. So the answer is 169.37. So the matrix D1L D2L is nothing but this. You have by A. Now, finally, what we need to solve is this system, right? So we need to solve this system. What is the system that we need to solve? It is 4, 2.828, 2.828, 19.313 acting on x1, x2 is equal to 0, 169 point. So let us solve this system. We get from the first condition, we get x2 or x1 is equal to minus x2 into 2.828 by 4. Substitute this in the second equation, we get 2.828 into minus 2.828 by 4x2 plus 19.313 x2 is equal to 169. So that brings us to the end of today's session. Thank you everyone for attending.